When we think about optimization, we usually picture this hunt for the one single best answer, right? The fastest car, the strongest bridge, the most efficient algorithm. But what if the goal wasn't to find one perfect solution, but an entire universe of really great ones? Okay, let's dive into this powerful idea called quality diversity. So here's what we've got lined up. First, we're going to question this whole idea of a single best solution. Then we'll get into the massive challenge of solving thousands of problems at once. After that, we'll uncover a much smarter way to search for answers, peek at the algorithm's secret sauce, and see how robots put it all to the test. And finally, we'll wrap up by looking at what this could all mean for the future of optimization.
All right, let's kick things off with a question that really reframes this whole field. Seriously, think about it. Sometimes what you really want is a whole menu of high-performing options, each one different from the last. Maybe one design is the most efficient, but another one is way more durable, and a third just looks better. Having a bunch of great choices is often way more valuable than having just one so-called perfect one.
And this is exactly what quality diversity algorithms, let's call them QD for short, are built to do. Instead of just climbing one mountain to find its peak, a QD algorithm is more like an explorer mapping an entire mountain range, trying to find the highest point on every single peak. The goal is to build this rich library of solutions that are both excellent, that's the quality, and super varied, and that's the diversity. And this isn't just some abstract idea, it's got some really cool real-world uses. People have used QD to evolve whole repertoires of walking styles for robots, to design collections of high-speed bicycles with all sorts of different shapes, and even to automatically generate endless varieties of cool video game levels. In every one of these cases, the goal isn't just one answer, but a whole toolbox of creative options to pick from. But here's the thing. Traditional quality diversity algorithms, they hit a massive wall when the problem gets even more complicated. See, standard QD is awesome when you're solving one fixed task, like finding different ways for a healthy robot to walk. But what happens when the task itself is always shifting? What if we don't have just one robot, but thousands of different ones, and each one has its own little quirk? This slide really gets to the heart of it. Finding a good walking style for this standard hexapod robot, that's one problem. But finding a unique, high-performing walk for 2,000 different versions of this robot, say one with a slightly shorter leg, another with a busted joint, that is a challenge on a completely different level. And this isn't just for fun. It's the key to making robots that can actually adapt and recover when things go wrong in the real world. Now, the brute force way to do this would be to take every possible walking style and test it on every single one of those 2,000 robot variations. And as you can probably guess, that is just computationally insane. It would take a ridiculous amount of time and processing power. Basically, the search would grind to a halt before it even got started. But this is where the research we're looking at today introduces this, well, it's a beautifully simple yet incredibly powerful idea. The core idea here is that these tasks aren't just random, disconnected islands. A great solution for a robot with one leg that's a little short is probably not all that different from a great solution for a robot where that same leg is just a tiny bit shorter. They're related, they're part of a family. So here's the crucial insight. We can use those similarities between tasks to our advantage. By trying to solve all of them at the same time and letting them share information, we can find fantastic solutions for every single task, way, way faster than if we tried to solve each one from scratch. This change in thinking just blows the doors open to problems that were way too big to even think about before. Okay, so how does this new algorithm, multitask mapped elites, actually pull this off? Let's pop the hood and take a look. It's a really elegant loop. First, it takes good solutions it's already found, these are called elites, and it kind of mixes and matches them to create a new candidate. Now, here's the genius part. Instead of testing this new solution on just any random task, it intelligently picks a task that's similar to the ones its parents were good at. Then it runs the test on just that one task. And hey, if it's a new champion for that specific task, it gets added to our big collection, our map of elite solutions. The real magic behind that intelligent selection step is a clever little tool for machine learning called a multi-armed bandit algorithm. Just imagine a gambler trying to figure out which slot machine in a casino pays out the most. The algorithm is constantly learning how close it should look for a new task to test. It's always balancing exploiting what it knows works by picking very similar tasks with exploring new possibilities by sometimes picking tasks that are a bit further away. This lets it adapt all by itself, no manual tweaking needed. Okay, so the theory sounds fantastic, but does it actually work in practice? Well, the researchers put it through its paces with two really tough robotic experiments. So the first test involved a simple little robot arm. The goal was to find the right joint angles to reach a target. But here was the twist. There weren't one, but 5,000 different versions of the arm, each with different lengths and joint limits. And the results are just, wow, they're so clear when you see them. On the left, that's the map of solutions found by Multitask Map Elites. See how smooth and consistently bright yellow it is? That means it's finding great solutions across the board. Now look at the right. That's what you get from a standard powerful optimizer, in this case CMA-ES, run on each task one by one. It's a mess, right? It's noisy, it's inconsistent with all those dark patches of bad performance. The difference is just night and day. This bar chart puts some hard numbers to what we just saw. Looking at the average performance or fitness across all 5,000 tasks, the solutions from Multitask Map Elites were way, way better than both the one-by-one approach and just a random search. It wasn't just a little bit better, it was in a completely different league. For the second challenge, the researchers really cranked up the difficulty with this hexapod robot. The task? Find the fastest possible walking gait for 2,000 different robot bodies, each with randomly different leg lengths. This is a much tougher problem, with a huge 36-dimensional search space to explore. And in this much harder test, the results were even more dramatic. Multitask Map Elites was able to discover high-performing walks for all sorts of robot bodies. And the standard approach of running an optimizer for each of the 2,000 tasks separately, it pretty much failed completely. With the same amount of computer time, it just couldn't find good solutions. This really shows that for complex, real-world problems like this, the old one-at-a-time method just doesn't work.
So, what's the big deal? What does all this mean? Let's zoom out and look at the bigger picture.
The huge takeaway is this. We can now move from solving one problem at a time to solving thousands of them. This research gives us a practical tool to efficiently generate a whole catalog of high-quality, diverse solutions for an entire family of related challenges, all in one single run. And that leaves us with a really exciting question to ponder. Just imagine, what problems could we solve? Personalized medicines, custom-designed engineering parts, or even adaptive robots that can handle any damage thrown at them. What new frontiers could we possibly explore if finding 1,000 specialized, amazing solutions was suddenly just as easy as finding a single one? The possibilities are pretty mind-blowing.